Welcome to Wireless Future. We are back with another episode where we will answer questions that we have received in different social media. And I'm Emil Björnsson, and I will answer them together with Eric Larson. Are you with me on the call?
Oh yeah, hi Emil. How are you today?
I'm great. And today we have sort of tried to gather questions that are particularly focused on reconfigurable intelligent surfaces, which is a topic that we have covered in the previous episode. But let me start with asking you a question, in more general. Why are people talking about 6G already now when 5G has barely been released?
Oh, that's a good question. I don't know if I know the answer. I mean, I suppose that, if you are in research or development for that matter, you always think about what's coming next, right? And I do think, although 5G has not been deployed everywhere, it does seem that the standards are maturing and being finalized, so that it does make sense to look out for the next thing that we'd be working on. Do you have a different answer?
No, I think you're totally right. And I think when it comes to the timeline of the development, it's sort of 10 years ago, people started to come up with the ideas of the main new features of 5G, like massive MIMO and the use of millimeter wave bands and things like that. And then it takes a few years for people to start to understand which are the different ideas that fly and which will not really work out so well in practice. And then you can start with standardization and doing all the work that comes to that, and then building products. And then eventually, after 10 years, you're actually done with something that can be used in real life.
Yeah, and I suppose there are also emerging new technologies that are sometimes foreseen as components of future generation wireless. I mean, reconfigurable intelligent surfaces, that'll be the topic of the Q&A today, might be one of those. I mean, or at least is sometimes argued to be one of those. So there might also be, a thing here that new technology is emerging and one sees the potential to exploit those for future generations, and just the sheer fact that there are new technologies emerging then that pushes the need or the desire for a new generation of systems or of standards.
Yeah, so reconfigurable intelligent surfaces, or RIS as we abbreviate it. So this is, in a nutshell, that you have a surface with reconfigurable properties that are reflecting or interacting with radio waves that are transmitted from other places, so that they, for example, can be directed towards the receiver and improve some kind of propagation conditions and things like that. And when people are claiming that this is a 6G technology, is that something that we can already say today that that's true?
Oh, you mean whether the reconfigurable intelligent surfaces are 6G technology?
Yeah, is that sort of a core feature of 6G?
I would think rather probably not. I mean, this reconfigurable surface technology might be there as a component for certain niche use cases, but I'd hardly think it is a cornerstone technology. I think active surfaces, this massive MIMO the way we know it, and its incarnation in terms of distributed or cell-free setups, also known as P-cell and radio weaves and radio stripes and all that will be the cornerstone 6G physical layer technology. Antennas spread out and integrated into the environment in the form of perhaps large intelligent surfaces, but active surfaces, not reflecting surfaces.
Yeah, so it's definitely too early to call which technologies that will be in 6G and which will not, but it's so far I think there is still a long way to go before we can demonstrate that these surfaces are so important that there will be a cornerstone of 6G and solve real problems that we haven't identified what are the problems that 6G needs to solve as compared to 5G.
Yeah, I'd also think so. So do you think we should move on with the
questions?
We can
take next question.
Yeah, I think the first question here was on materials that are used for these reconfigurable intelligent surfaces. And so what kind of materials that are used? You want to go on that one?
Yes, so that depends a lot on what frequency ranges we are looking for, because these surfaces might have particularly been developed to be used in optical ranges or near optical ranges, but now when people are talking about them in wireless communications, it's more of use cases in the conventional radio frequencies like 3 or 30 gigahertz, those type of 5G frequencies. And there, I think the materials that you could imagine is that you have a big surface with some metal behind it, some copper plate, and then you have discrete elements. Each of them will be sort of like a simple electrical circuit. So some lumped electronic elements, transmission line or something like that connected with a diode. It could be a switch diode that can switch between two different states, and in that way it will sort of filter the incoming signal in different ways depending on which state it is. Or it can be a varactor diode that could sort of more continuously change its capacitance and then change in a continuous way how it interacts with radio waves. Then if you go up in frequency, graphene or ceramic composite materials, there are a number of different materials that people are considering.
But are these really, new or modern materials? It sounds like mostly classical electronics, right? Do we know that? Or is there like some cutting edge material science or technology that enters into the design of these surfaces?
I think that there are some cutting edge variations of these things when you really go into the chemistry behind it. I mean, when it comes to frying pans, we have Teflon materials there for a long time, but variations on the same kind of concept can be there. But then I think the important thing is that you will like to be able to change the properties, not only have unusual properties, but change them, change impedances and things like that over time and control it and print a big surface in a affordable manner with many small elements that all are controlled. And that is a real challenge.
Right, so I'm still using the cast iron, by the way. But I see here, that the electronics behind might be based on known principles, but it does use like state-of-the-art circuit technology, obviously, to perform the switching and so forth.
Yeah. Yeah, and there is a wide range of materials that people are considering, and they all have their pros and cons in terms of how they are behaving in different aspects. How well you can control it's sort of the delays that they are creating, and also what the price is to pay in terms of the amplitude losses and things like that. Okay. So the next question we got was probably spurred by the fact that our last episode on reconfigurable intelligent surfaces was about myths in that topic. And we got the question, why are researchers wasting their energy and resources working on RAS when it's obvious that it cannot provide significant gains, like 10 times compared to other existing technologies?
Oh, yeah. So I think the question had several parts, right? Is it obvious that it can't provide 10 times gain? I'm not sure. There might be niche use cases where you can actually get a lot of gain if you're in the immediate near field, for example, and you want to form a beam, and then you can adjust the impedance of these small reflecting atoms that are in the immediate vicinity. But by and large, I think that the gain, at least if you are like in the mid-far field of the surface, then the gains are not very high, and specifically using intelligent surfaces to improve the SNR doesn't seem to be very viable. They might be useful to improve the rank of the propagation channel by like creating an additional path. So if you're like rank starved, and which is typically in line of sight the case, then it's definitely possible you could create another path which would give you like another, say, singular value of your channel matrix, and which would in turn give you an increase in multiplexing gain. But it's hard to see that that would be much, that the sea surfaces would be a much more efficient or better way of doing that than using, say, conventional relay, which I think is suggested in the question, is a fairly mature technology. So then the other part of the question was why folks are working on this. Well, it is an exciting technology, I think, right? I mean, there's opportunity to do some good science here, to write papers with interesting mathematics and so forth, to do experiments and break new grounds and explore technology that mankind has not yet experimented with. And who knows, in the process, I mean, there might be spin-offs that are discovered and invented that are useful. And there might also be that there are some niche use cases where this technology really is going to break the deal. So I think it is a mix here of curiosity and not knowing the real potential for certain niche cases. And perhaps to some extent just that, well, it's new, let's work on it and let's put our grad students to write papers on it and apply, all the knowledge that we have in comms theory and so forth to produce more academic papers.
Yeah, so sort of in academia, one of our core roles as compared to a industry company is that we should work with basic science. And here there's a lot of basic research in terms of material science and how to build these surfaces. And then it sort of challenges the way that we are used to building communication systems according to the communication theory. And then there are new interesting problems there to solve. And I think what we tried to say with the previous episode is that if the use case would be to just improve the signal to noise ratio, then there might be other solutions that is doing that in a better way that is already available. But if we can identify some other metric, then it could be a great use case. And then we can see how often that metric really matters.
Yeah. And again, I mean, relating, I think we talked about this a couple of weeks ago on the podcast, that suppose that this technology became really scalable and cheap so we could cover the walls, like, I mean, the Hall of Mirrors in the Castle of Versailles with reflecting surfaces, and really control the propagation environment and solve all the issues with channel estimation and all that. Sure, I mean, you'd probably be able to improve on the propagation conditions substantially. But the question is that is that a viable, compared to the fact that, or compared to existing technology, most importantly relaying in its different flavors, right? I mean, full duplex relaying and MIMO relaying and so forth. Is this a cost-effective technology? That stands to reason, I think. And my bet would be that it's probably not, but let the future tell.
Yeah, I agree.
So I think on the same theme, there was a question here on when do you think that reflecting intelligence surface technology can beat relaying?
Yes.
Do we, I mean, perhaps you could have a go on that, Emil. I mean,
yes, so I have some thoughts. So I think that generally what you should think about is that we are sort of building a surface that is not amplifying signals. So we are getting rid of power amplifiers, but we need to pay by making them physically large instead. And then if that was the only thing, okay, we trade power amplifiers towards size, well then that is what we have shown, that you get approximately the same as now, but you need to give something that's much larger. But if we can also think about, can we use this large surface area to do something that a small relay can't do? Well, you were touching upon this type of thing, that we could add additional propagation paths, and that will improve the rank of the channel, and in that way we can send one signal directly and one via the surface or something like that, or multiplex multiple users. So that is one use case. Then when it comes to things like shadow fading effects, particularly when you go up in frequency, the risk is that you're blocking the signal And if the surface is large, hopefully some piece of the surface will see the device in a good way, and that will help out with that one. And then one specific thing that a surface like this can do is also to change the polarization of radio waves. And for an IoT device that you put up somewhere, it's going to be fixed there forever. And if you're unlucky, it has the wrong polarization compared to the signals that are going to reach it. But then this surface can rotate the diagram and improve the signal conditions a lot.
So I really think of reflecting intelligence surface as a large full duplex MIMO relay without amplification, right?
Yeah.
Yeah,
exactly.
Well, okay. Do we want to move on through the list here?
What are appropriate channel models when considering RS systems?
Yeah, see if I could answer that. So I think that if this technology is going to be useful ever, it's likely to be in cases where we have line of sight, at least line of sight between the transmitter and the surface. And it's also possible, that the transmitter will be in the near field, right? So we'll probably have some sort of line of sight, possibly near field model that in turn would have to be crafted carefully if we work with it mathematically. I don't think that we could use all these canonical propagation models that we had in the massive MIMO literature with independent Rayleigh fading, correlated Rayleigh fading and all that. I think we probably have to look closer at the physics here to really make sure to capture all the effects. And it's also possible that depending on the atoms in the surface, how close to one another they are located, they would have to deal with and model the electromagnetic coupling effects and all that properly. So the closer to the physics we can get, the better, right? But again, I tend to think that we probably would be, at least one of the links here would be in line of sight and possibly in near field. So that have to be modeled properly. Do you have any other answer?
No, I think that it's sort of, we need to think about what the setup is, as you were saying, and then we can use essentially the same type of modeling because it's the same frequency range, it's the same kind of objects around there, but we need to think about what are the particular properties that this surface is adding. And in a lot of research, it's like if you don't want to assume a channel model, you assume IID Rayleigh fading or independent Rayleigh fading, and that is something that can only occur in practice if you have a one-dimensional array where the elements are like a half a wavelength apart, and then under rich scattering conditions you get this kind of model. And I think that has been fine for a long time, but now we have a surface that is categorized by being two-dimensional and having element spacings that are smaller than half the wavelength. Then these are two reasons why this IID Rayleigh fading model can never ever appear together with these surfaces. So there are other models to utilize. We should just stay away from that particular model because it can't physically occur.
Yeah, I think that's probably true for many other models as well. I doubt that correlated Rayleigh fading would be a good model for these for reflecting surfaces either. I think you'd really have to look closely at the physics, and also you'd have to look at it from a case-by-case on a case-by-case basis. Is the transmitter in the near field or not? Is the receiver in the near field or not? How large is the surface compared to, is it a small piece on the wall in a big room, or is it the whole wall in a room that has a lot of other objects that contribute to the propagation and scattering? So I'm not sure there is a one-fits-all model here. I think one really has to look on a case-by-case basis.
Yeah, no, so I think what I was trying to say is that we need to consider spatial correlation of channels. Then the Rayleigh fading, which is sort of assuming that we have many more scattering elements in our propagation environment than the size of the surface, that part might break down, so we won't have a Gaussian distributed channel anymore. That won't be a good model.
Yeah, it's very, very possible, yeah.
Okay.
Yeah. Okay. So I'll move on in the list, and there's a next question here on what is the difference between reflecting intelligent surface technology and holographic MIMO?
Yes, so this is a good question that I think can create a lot of confusion because people like to categorize things differently in the literature. I think that I will try to categorize these as two distinctly different things, and I will explain what that means. So a reconfigurable intelligent surface would be something that is placed in between the transmitter and the receiver and have all these properties that we were describing. Then in holographic MIMO, the idea is that the surface is part of the transmitter or part of the receiver. So it could be that you are putting a signal generator behind the surface, and then the signals are going through a lot of different elements that are filtering them, and then in this way you can generate beams that are pointing in different directions. And this type of technology is already out there. It's being used for building satellite receivers or building I think some millimeter wave transceivers are also built in this particular way. And sort of it's called holographic because it's sort of built on the same principle as holography, that you have a surface with certain properties, and then you illuminate it, in this case with an RF signal, and then the surface is shaping it so the signal looks in a particular way.
Right, so the holographic is more like an active transmitter, whereas the reflecting, as the name suggests, is a mirror, right? Or it reflects the signal, yeah.
Yes, but then there are some proponent of reconfigurable intelligent surfaces that likes to view it as like an umbrella term for everything that has to do with this type of surfaces, so that could cause some confusion. Then they categorize holographic MIMO as a special case under it. But I like to keep them separate because building holographic MIMO type of things is something that already there are products on, but the real challenge is to build these ones that are separated.
Yeah. Okay, do you want to move on? There's a question here on how deep learning can be utilized in reflecting intelligent surface systems. You want to answer that?
Yeah, I can answer that. So I think there is still a lot of research that can be done around that, but I think as always when it comes to deep learning or machine learning, this is something that can be applicable when there is characteristics that are hard to model. And I think that when it comes to learning the propagation environment, this might be one of the challenges that we talked about in a previous episode as well. That you put them out in a particular area and in a room, for example, and then when the surface gets large, there is so many different dimensions that you need to learn in order to figure out where to reflect the signal and where to focus the signal and so. And if you would like to sort of try to reduce the dimension of the channels that you would like to estimate, then you could potentially try to learn characteristics of the room, so you know that users can only be at certain locations, or at least they're more likely to be there, so then we should search for them there first. And these type of local propagation conditions that only are accurate in a particular deployment scenario, but you can sort of tune it for every deployment. Then you were touching upon the mutual coupling and these type of effects, and I think that could be important as well, that we have hardware effects in the surface that are hard to model. We could neglect mutual coupling and say that we can mathematically compute the array response for a big surface like this, but then we have put mutual coupling into it and we don't know what the array response will look like anymore, and then as we are switching between different different properties in different elements, this is also affecting the mutual coupling and a lot of other effects that are hard to model. Maybe if you switch to different elements to the same state, they will not behave in exactly the same way. So there are many things that can be learned there, how they would actually behave. And also when it comes to sort of configuring a big surface like this, say that you have 2,000 elements, each of them can have 1 out of 4 states. Then you quickly get a huge number of different types of states that you can choose between, and solving the optimization problems there is mathematically possible, but will take forever. So maybe one can design algorithms that are helped by learning shortcuts.
So basically, you're suggesting that learning could be used to circumvent or avoid the need for accurate physical modeling. That's number one. Number two is it could be used for to help in solving certain optimization problems. And number three is it could be really, used to learn what the propagation characteristics look like and where the users are more likely to be located, so that the system could be optimized to function at its best when the users are where the algorithm thinks they are, say. Yeah. Sure. Sounds like a direction with possibly some potential for good development.
Okay, so next question. Can we use the channel estimation from uplink also in the downlink when using these surfaces?
I think so. Isn't this just the usual question on reciprocity? If we are in time division duplexing, then reciprocity holds to a very good degree of approximation or accuracy, and then uplink and downlink channels are identical. So then the fact that there is a reflecting surface or not present doesn't change that fact. And in FDD, that's less clear. Maybe the angles are the same. So the channel response from uplink could be transferred or mapped onto a channel response for downlink somehow using appropriate algorithms. That remains to be really proven. But in principle, it could work, perhaps. I'm not sure. Is that?
Yeah.
So do you think there's something else here hidden in the question?
I think there is something else in addition to that. So the propagation channels to and from the surface are going to be reciprocal. But then I think this surface can, if you want to, be designed so that it's not entirely reciprocal. So it could be like that if the signal comes in from one angle, it will behave differently as if it comes in from another angle, and it will reflect the signal in a slightly different way. So in that way, its frequency response will be dependent on the incident angle, and then it's not entirely reciprocal anymore.
Oh, I didn't know that. So you're suggesting that the surface could be designed in a way that the reciprocity theorem of electromagnetics doesn't hold anymore. It's possible. I don't know. I have to read up on that, I suppose. I think to break the reciprocity, typically you need some exotic ferromagnetic materials or other strange things. But if you put that into the surface, who knows?
I don't know exactly how this is done, but I've understood that one could build the surfaces to break reciprocity if you really want to.
Yeah, I think let's come back to that question perhaps at a later in a later episode. Again, I thought reciprocity was there. Unless you had very strange materials in the vicinity. But on the other hand, the surfaces are built from materials that have very advanced properties. So we'll have to check back on that, I think. Maybe let's move on to next question here is on how quickly we can switch between different configurations in a surface.
Yes, so I've been searching for some literature around these type of things because I think it's important to understand that if you're going to build a system that is switching and following different users, and there are different parts of this. So if you go down to the actual hardware, if you control a element with a diode with two different elements, two different states, then it can take just a few nanoseconds to switch from one to the other. And I'm not entirely sure about the transient effects, but suppose that they are also small, then nanoseconds is not much. But then if you build a control circuit that is going to control, say, 100 of these elements, and then they're going to choose between different states, and they're going to be a whole sequence of things, and maybe they're going to switch from sequentially, for example. In the paper that I found about that, it took rather microseconds, up to 10 microseconds to switch 100 elements. So that's also not very much. I think what is really important here is rather how we are sending our communication signals. So if you are creating a analog signal using pulse amplitude modulation. We have a sequence of signals that we want to transmit. We multiply each with a pulse form, and then we transmit them one pulse after the other at a certain distance between them. And these pulses are normally overlapping. So if we're going to change the state and we don't want to mess with the orthogonality between different pulses, then we would like to have some kind of separation between one pulse and the next pulse, which we don't normally have. So if we have a raised cosine pulse with 0.5 roll-off, then the next one is, and you jump over one pulse, so you have a guard interval there, then two pulses will be not overlapping anymore, and maybe we will have to have some kind of guard time intervals when we are switching, just to get rid of weird effects that happens in between.
Yeah, so I'm thinking, I mean, all this switching, couldn't that generate nasty side effects? Because the switching is like a multiplicative effect, right? It comes on top of your waveform. So you take a waveform in, say, continuous time, well-defined, nice waveform that occupies some given spectrum frequency band. And then you add this switching. It's like multiplying this waveform with something that changes over time. So multiplication in time domain is convolution in frequency domain, right? So we see a broadening of the frequency spectrum, which number one is undecided, because I mean energy will leak outside, and number two, that leakage could cause out of band emissions potentially. And you talked about like switching here on the time scale of a nanosecond. So nanosecond is 10 to the minus 9, so that's 1 gigahertz, right? So couldn't one potentially generate a lot of out of band EMC problematic interference here? Or is it that this interference dies off so quickly with distance that nobody will ever notice it?
Yeah, so I think in any case you want to put in some kind of silence when you are switching, just because you cannot trust the signals that you're receiving that are transmitted while you're switching, because weird effects can happen. And then, as you said, other band effects is something that's is interesting there as well. If it's actually going to create a lot of interference, then you will have to be silent. And more generally, I think this is also a standardization question. If this is going to be used, if you have materials that you are changing in its properties at a fast pace, you're not only changing the propagation environment inside your band, you're also changing it in a wider frequency range. So you might be creating small-scale fading in another operator's band.
Yeah, that's not really true. I mean, but again, returning to the switching, I'm thinking think of a square wave with duty cycle 1 nanosecond. So that'll give you harmonics at a gigahertz and then multiples of the gigahertz, right? And depending on how the switch is actually implemented here, the harmonics, the amplitude might fall off faster or not so fast with frequency. So it seems to me that this will have to be very carefully crafted not to create problems in neighboring bands. Yeah. All right. So the next question is on experiments, whether we've seen any experiments of real-time control of reflecting reconfigurable intelligent surfaces. You want to answer that?
Yes, I can answer that, because I recently found a very nice video from the University of Surrey in the UK, where they are showing how they are reconfiguring a surface. And I think that might be the first real-time demonstration. There are some papers that are describing measurements from before, but then typically they have sort of already crafted that the transmitter is at a given location, which is in the focal point of the surface. Here they're putting up the surface in the room, the transmitter and receiver at some seemingly arbitrary locations, and then as they are moving around the surface, they are pressing a button on a tablet, and then they are reconfiguring the surface. And you can see in the video how they are improving the SNR by, say, 15 decibels when they are having the right configuration. And I talked with the people that have done these experiments, and they're using 3.5 gigahertz band. They have 2,500 elements. They are like a 0.15 times the wavelength in maximum size, and it seems to be a nice step towards actually building something along this way.
Yeah, really. I mean, so how large were the gains you said quantitatively here?
So I think they were seeing that when they turn on the surface, and if you compare having it turned off with having it turned on, you get 15 decibels improvements.
15 dB, that's a lot. I mean, so
that's a lot.
Compared to not having the surface then.
Then it's hard to quantify these things properly as well, because they're using a horn antenna for the transmitter and the horn antenna for the receiver, so they have very narrow angular windows where you can pick up signals. So it's hard to know if you would optimally design this surface. Will you get 15 dB or will you get much more? Is it just that they were able to roughly reflect the signal in the right direction so that something went into the horn antenna, and that they had so short distances that you get 15 decibels? It's hard to evaluate.
Right, so we're really getting back to what we talked about earlier, right? That this seems to be a really niche use case. We have a horn antenna, and definitely you can find niche use cases where you get significant gains. I guess it remains to be seen whether those gains can be obtained in more general setups or under more general circumstances.
Yeah, and there are these classical use cases of reflecting surfaces that are not dynamic, that you put up in the countryside to reflect the signal from one hill down to a shadowed valley. You just put up a big billboard, and then you need to design the billboard so that you roughly are putting energy down in the valley. And with the surfaces, you sort of will try to do the same thing, but you focus it more. You can decide on where it should be put, and then you can sort of narrow down the area where the size of the beam.
Right. Yeah, that's also. I mean, again, I think it's a niche use case, right? Although it's an interesting application, no doubt.
Okay, so I think we have a few more questions, and these are a little bit related to reconfigurable surfaces, but also to maybe research methodology. So it says like this: your paper on 3 myths about reconfigurable intelligent surfaces identifies some misleading statements in several highly cited papers. But many researchers continue to read, cite, and build new research on those papers. What can the community do to mitigate these problems that myths are propagating?
Yeah, good question. I mean, I think it's our joint paper that's referred to here, right? The 3 myths on reconfigurable intelligent surfaces or something like that is published in the Communications magazine.
In the December issue to 2020, I think it's...
Yeah, it is, right. So, no, I mean, it's true that there have been a few cock and bull statements made on path loss of reflecting surfaces and I think a few other things. And, I mean, the point here is that these are no real controversial matters, right? I mean, this is all basic electromagnetics. You pick up your college textbook, Classical Electromagnetic Radiation by Halden Marion is the one that I had myself in college. And it all follows, I mean, from, say, basic considerations starting off from Maxwell's equations. So I think one thing that ought to be done is just to train students in physics and in rigorous thinking based on physics. And another thing might be to, we just have to be honest in our papers, right? And not be afraid of pointing out when something is, say, wrong elsewhere. Which is, I suppose, partly also the motivation behind the myth paper. What do you think, Emil, should be done?
Yeah, I think we are coming to a point in our research field where we need to start also consider that not everything that you read is right. And I think that since a lot of our communication theory have been built on sort of accurate models and rigorous mathematical arguments and things like that, then we are used to saying that, well, if the math looks right and they are building on the right models and everything is right. But then in many other research fields, it's more like you throw out a hypothesis, you provide a first experiment related to that one, and then the hypothesis is not true unless it has been validated 10 times by others. And we might come to a point in our research field as well with papers being uploaded as preprints. People want to be fast with putting out the first hypothesis about something. And then we also need to acknowledge that some of these things that people will put out are not right. And people need to be critically reading all of these arguments.
Yeah, critical readers, perhaps critical commenters as well, right? And I think, there is, I think, some tradition in our field of authors publishing a correction when they or someone else have discovered errors in their papers. It's very rare that papers are retracted. I mean, it happens routinely in other fields, right? I mean, that was, for example, if I remember well, was it the New England Journal of Medicine, or was it the Lancet that published a paper on hydrochloroquine as a treatment for COVID, and the claim was that hydrochloroquine was harmful, but it turned out that the data in the paper could not be validated. So the authors retracted the paper, and that's like unheard almost of, I think, in the comms theory field, right? I'm not sure.
Yeah, I think it's very seldom that other people are publishing comments on papers. What happens occasionally is that the authors are correcting something, but then it's really up to the authors to admit that something is wrong and actually correcting that, which I think is giving much more credibility to the person than actually just pretending as if an error wasn't there and that they didn't mean what was written in the paper and things like that.
Of course, yeah, it does. I mean, and I think this really becomes an issue when, say, high visibility papers or papers in highly visible venues and journals are wrong, and where papers with foundational errors attract a lot of followers. There's always going to be a lot of noise out there, and perhaps the best approach is just to ignore the noise or neglect the noise. But you're right. I mean, there is an issue here, I think, with research methodology, and perhaps the desire to be the first and have the most papers and have the most citations and all that.
Exactly, and I think it also comes together now with when there is a push towards open publishing. Even IEEE is creating new open journals, and they want to attract authors by having a faster review process, which also means that faster is less rigorous. And I think we were noticing these issues like 1.5 years ago, and we started to write papers and try to publish them in the conventional venues and things like that. And then we got out published by people publishing in open journals that had like a few weeks of review processes. So it's hard to keep up when there is so much noise appearing.
But it is a good question in general. I mean, how is academic publishing likely to evolve in the next few decades? Perhaps that's something we should return to at a future point in time.
Yeah,
Emil.
definitely.
And yeah, well, okay, so
I think we are reaching the end of this set of questions and answers, and we are very thankful for the questions that we have received so far, and we will probably ask you for additional questions, or please always ask questions related to our videos, and we might pick them up in future Q&A episodes. So with that, thank you for listening to this episode.
Yep, thanks a lot, and bye-bye.
Bye.